today? What do you have on your head? Okay. You had a busy week, huh? Quality, analysis, chemistry, food engineering. That's BBE, food engineering, right? So, wow, it was a very productive week for you guys. I have a question for you, if you let me ask it. Quietness in the room is wonderful. The quiz is, not quiz, your exam and food analysis is not this Monday, the following Monday. Do you have any tests on the same day? Perfect, so you can study. What are you trying to ask? Push it back a week? Let's vote on this.
Why? What's the week after? The week after is nothing. No, we have our final from like, yeah, when we have it set up.
Molecular's on the 24th.
And this exam is the day before.
Okay. Let's vote on this.
Hold on, let me get the...
So it's not this Monday, right? It's the following Monday. So the 23rd. Here are the two options that I heard. The 25th? Or... Okay. Let's vote. Let's vote. We'll go with the majority. Monday, the 30th.
Question. What does our class schedule look like? Yeah, is it a partial or full?
I don't want to do Monday. Monday the 20th.
Usually, if there is anything due on Monday, it would be a short lab report. Okay. I didn't see enough hands up. If I don't see enough hands up on either days, it will remain on the 23rd. Ask again. Who wants to move it 1 week? Raise your hand. Okay, that's not a lot of people. Huh? 1, 2, 3, 4, 5, 6, help me count. 7, 8, 9, 10, 11, 12, 13, 14. That's only 14 of 43 people.
See how many vote the others.
Who wants 25th? 25th? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 and 14, that's not majority of the class. It will remain on the 23rd. Okay. I'm sorry, I tried. What? I can't. If not more than half the class, it's not fair. I cannot please one minority over another minority. So I can't do that. If you change your mind and ask again, think about it. I can ask again on Monday. Okay. All right, let's get going with the lecture. I forgot what we're doing. Okay. No, guys. Myson, you're great. Thank you. Okay. Let's get going. So I have few questions as recap because we didn't go far in the lecture, and these are for next time. So what are the different species of matter that can be analyzed using spectroscopy? Different species of matter. Yes, Dad? There's actually two species of matter. Either or. atoms or molecules. So like in atomic absorption, you measure the elements in their atomic form. That's called atomic absorption, measuring the interaction of atoms with light. And then you have the molecule, where the molecule itself interacts with light. All right, name the different forms of radiation or matter, radiation and matter interactions. Or one of them, or two of them. Name any types. Wow. So it's been a tough week, huh? Okay, go ahead. Okay, so before fluorescence there's absorption. So light can be absorbed, okay? Light can be emitted. Okay, I'll go with that. Brad? Refraction, like in refractive index, Katie. Diffraction of light when the light breaks into individual wavelengths. Was there? Yeah, there's one more. Scattering of light. I'll take that. Scattering of light. There's one more then. Interference, and we'll talk about it more when we cover the IR lecture. When wavelengths meet, two different waves meet, and then it either can be constructive or destructive interference. Okay. What are the spectral regions most relevant to food analysis? Yes, Lauren. UV and IR? And visible. Thank you. And here they are. So this is the visible range. I keep forgetting. My Senor, my angel. I always ask you for things, but can you remind me to get batteries or get me batteries for this? Somebody has to remind me. I'm just going to not remember. Okay. So this is the visible range. It goes usually from 400 to 800. It depends on how it's reported. Some people, you'll see it 400 to 750, but the general or known range is 400 to 800 nanometer. So that's the range for the visible. And then the infrared is slightly shorter wavelengths, and they carry higher energy. So remember this, the shorter the wavelengths, the higher energy it carries, because think about the frequency. How many oscillations per unit time? So the higher the frequency of the wavelengths, the higher is the energy, and the shorter is the wavelength. So infrared would be slightly longer and carries a little bit less energy. These are the main regions that are used often in analysis of food. So when we deal with light and usually absorption and emission of light, we better refer to it as photon of light rather than a wave of light. We talked about last time about how the particular property and the wave-like properties. So when we're dealing with absorption and emission, we always refer to it as absorption of photon of light and emission of a photon of light, or pockets of energy. Okay. The simplest form of absorption and emission is best explained when a photon of light hit an electron in a particular orbit. So when a photon of light hit an electron in an atom that is present in a ground state, that's the more stable ground state. So when a light hits that atom, the atom is going to get excited, and it's going to move to a higher orbit. So the whole atom, and if it is within a molecule, then the whole molecule is going to go from ground state to excited state. So the atom is going to carry more energy, right? There will be an increase in energy. So the whole atom is going to gain energy, and also if it's within a molecule, the molecule is going to gain energy. But this is not the stable form, and it won't stay like that. It's not going to be excited the whole time, so it's going to go back to the ground state. By doing so, the electron is going to jump back from the higher orbit to its original orbit. While it's doing so, it does two things. In general, it does two things. It always dissipate heat. So the energy that is released can either be all in the form of dissipated heat, or that particular atom within that molecule can emit radiation. So by doing so, the emission is when the electron goes back, and you always have a dissipation of heat. So less energy will be emitted as a photon. So your photon that is emitted, picture this, it has longer wavelength and less energy, right? So always, always, the emitted light has longer wavelength and less energy, because part of the energy that the atom gained was dissipated as heat. Okay? So oftentimes when you're reading a method, analytical method that is based on fluorescence, you're going to see in the method the absorption wavelength and the emission wavelength. They will describe. So the instrument was run at an absorption wavelength of and an emission wavelength of, because you have to absorb light at a particular wavelength, and then you'll detect the emission at the longer wavelength, right? If it is a fluorescence-based method. Would you like me to repeat any of this?
What are the two different ways that an atom releases energy when it absorbs the photon?
Dissipation of heat and dissipation of heat plus emission of photon. Yep. Okay. So this is basically what I explained. The atoms and molecules exist in their ground state. And when the atom or molecule is struck by a photon, may absorb the photon energy. Whatever the energy is carried by that photon is transmitted to that atom or molecule, exact amount of energy. Okay, that's that. Next point. Now this is the complex thought, is that the energy gained, or the change from ground to excited level to another excited higher level, is not a continuous scale. So it's not like 0, 0.1, 1, 2, 3, whatever continuous scale. It is discrete steps. So you have energy level 1, energy level 2, energy level 3, and they are discrete step, not continuous. So what does that mean? So every molecule or atom may absorb light at different wavelengths. Each wavelength will carry a particular energy, right? So one energy is going to probably take it from E0 to E1. That's the electronic level. It's called electronic because the electrons are moving from one orbit to the higher orbit. Okay, so it will go from E0 to 1. Another wavelength will give it another energy that could take it from E0 to E2. Okay? So it depends on the photon and the energy that this photon carries. That excitement can go from 0 to 1 or to 2 or to 3, depending on the orbits and the electrons that are absorbing the wavelength or the photon of light. So every atom and every molecule have its own set of energy levels, and it is not the same. So because it's not a continuous scale, every molecule and every atom will have different energy levels or amount of energy. Only that there is what we call allowable energy. So that's why there are atoms or molecules that don't absorb light at a particular wavelength. So you remember that spectra. So you have here nanometers for wavelength, and you have absorption. Let's say we're looking at UV. So some molecules, this is X, will not absorb in this region, 200 to 250. And then it starts absorbing here. Although the UV light is hitting that molecule, but this energy does not match the discrete energy of that particular atom or molecule. So if the energy does not match the allowable energy by the atom or the molecule, it will not take it, basically. Once the energy that hits is within its portions of energy levels, then it will absorb it. That's why this X here versus this is different. This absorbs light at 240, this one doesn't. So this molecule here has the same energy levels equivalent to the range of these wavelengths, 240. This one requires, let's say this is the caffeine, 272. The wavelength that is 272 carries the same allowable energy that the molecule can absorb. Good? Okay. Remember the allowable energy term, then you'll understand it a little better. Okay, so we have different types of energy. We have electronic energy, vibrational, and rotational. The electronic energy is the energy that is absorbed by the electron, taken on, hits the electron, and the electron moves to a higher orbit. The vibrational energy is the vibration of the bonds, the molecular bonds. They're always in vibrating movement. They stretch, they bend. So the stretching and the bending of the bonds will increase when there is an absorption of energy within that region. And you can see here the vibration energy is smaller than the electronic energy. IR, remember IR radiation, does it carry more energy or less energy than UV radiation? What? One by one. Carries less energy. Why? It's a longer wavelength, so it carries less energy, and hence the energy levels from 0 to V1 to V2 to V3, 4, 5, etc. are smaller than the energy the energy of the electronic energy. Rotational energy has to do with the microwave energy, and it is the rotation around the nucleus of the molecule. Okay, so because it's the microwave, it's a longer wavelength, so it carries less energy. So you can see the rotational energy are even smaller than the vibrational. So that's why it's superimposed on it. So again, this is what illustrates that electronic has to do with the electron moving to a higher orbit. Yes. So change in the potential energy of an electron will lead to change potential energy of the atom, and if the atom is in a molecule, also in the potential energy of the molecule. Okay, so this is explaining electronic energy. and the whole statement is just telling you that the energy is within the energy range of UV vis. The electronic energy is within the range of UV and visible radiation. That's all what it's saying here. Vibrational energy. So like I said, molecules are in constant motion due to the vibration of the bonds. And the energy associated is also quantized. That means you have allowable energy spacing. And then the energy difference between neighboring vibration energy are smaller. We already talked about that. They're smaller because of the fact that they're longer wavelength and therefore less energy. And the energy matches the energy of photons of the IR radiation. That's basically what I already said. And the vibration is the rotation of the molecule around its center of gravity. And the spacing levels are the same magnitude associated with microwave radiation, and they are smaller than vibration and smaller than electronic. That's because of the large or the long wavelength of microwave radiation. But in food analysis, we don't usually use microwave spectroscopy to measure components or to look at qualitative and quantitative data. So in food analysis, it's either UV vis or IR for spectroscopy analysis. So if we have an atom, the energy of the atom is equal to the electronic energy. There's nothing else. There is no bonds to vibrate, and there is no center of gravity for that atom. However, the molecule can pick up multiple different energy. If you're projecting light, that is all different sorts of light is hitting it, not just UV or vis, but also it's hitting, the light is consisting UV, vis, IR, and microwave is hitting, then the molecule can pick up energy from all these levels and go from an excited state to any position on the scale of its allowable energy. But if we're only projecting UV light on the molecule, then it will only have electronic energy. Please remember that. It can be a true or false question. So if we're only projecting UV light to the molecule, then we don't see this. There won't be a change in vibration and rotational energy. So this spacing of energy is unique to every molecule, as illustrated here, because they have different spacing of energy. Each will absorb light at different wavelength because they have allowable energy. And this helps in identification analysis, like we've seen in a previous lab, where each molecule will have a unique fingerprint of absorption due to its discrete allowable energy levels. So this is like two different compounds, the same as I illustrated here, because of the different energy pockets that it can absorb. Emission of radiation. So in other words, we call it fluorescence spectroscopy, and not all molecules or atoms fluoresce. That means most of the molecules or atoms will release energy as heat, dissipate heat, but some that will fluoresce will dissipate heat and emit radiation with longer wavelength and less energy. And that's very important to remember. Less energy and longer wavelength. Any questions about the concepts? Okay. This is lab next week. You already know what you're doing, so you will flip. So instead of doing LCMS, these groups will be doing AA next week, and the opposite for the others. We still have 20 minutes. I'm not going anywhere. On a Friday, talking about spectroscopy, really?
Gets the crowd going.
Gets the crowd going. All right, I have some recap. The recap question, we'll do it next time. So let's start here. Okay, see how much you remember out of this. Which is true? First of all, do you know what Beer's law? You never heard of it? No. Seriously?
I think we talked about it in like intro a really long time.
This is like fresh, I thought, like physics or something. I don't remember it, but I definitely learned it.
Yeah. Good, thank you. That's what I want to know. You've learned it at some point, so it will come back to you. So Beer's law, or really it's Beer's-Lambert law. I don't know why they dropped the guy, Lambert, because they both came up with this law. But it's only referred to as Beer's law. Did you hear it as Beer's-Lambert law?
Yeah.
Okay, then it's the author of our textbook chapter. I don't know why they dropped the Lambert. But it is Beer's-Lambert law. And anybody with any faint idea of what it is? Claire?
Absorption equals concentration times something.
That is the closest answer I've ever gotten in 10 years from anybody. Maybe she should get 2 participation points and a chocolate later. No, I'm serious. Give her 2. Yeah. Okay. There will be more of these during the semester. So don't feel you're unfortunate. So yes, it is absorption equal A times something times something. Concentration multiplied by absorptivity or molar extinction multiplied by the path length. The path length is if you put your sample in a cuvette, the light is going to go through that cell. So the traveling distance within that cell. So it is a linear relationship really between absorption and concentration. And that if you have a linear relationship, then you can measure concentration of an unknown based on its absorption. So that's why Beer's law made food analysis a wonderful tool, allowed it to happen. Without Beer's law, we would be lost. Literally lost. Okay. Can you guess then what is correct here? Wild guess. What? What? Elmo? No. Just what? Just B. Just B. And we're going to learn why it's just B. First of all, every analyte, we were just saying, they are unique. They absorb at different wavelengths. So they will have their own absorptivity. Molar extinction, molar absorptivity are the same thing. But if you only hear absorptivity or just absorptivity, that means the concentration is not in molar concentration. If the concentration is in molar concentration, then it's called the unit, or it's called molar extinction or molar absorptivity. Now, no, the incident beam minus exiting beam is not equal light absorbed. That's not a simple subtraction, and we'll talk about that. Katie. A and B. Well, A is correct by elimination, right? by process of elimination. You need a monochromatic light. That means you need a light with a singular wavelength for Beer's law not to deviate from Beer's law. Because absorptivity is specific to one wavelength. Because A and C. Because like I said, you need one wavelength for Beer's law to apply. Yeah, because absorptivity would be different. Yes, Riley. Huh? B was correct. Just B. Because molar extinction is not constant. Every analyte has a particular molar extinction at a particular wavelength. And yeah, with higher concentration, we'll talk about that. You'll deviate from Beer's law. And it's not a simple subtraction. It's a log of, it's a log relationship. And then here, it's A and C, because I was saying you need a singular wavelength light. Because if you have multiple wavelength light, you won't have a singular absorptivity, because each molecule will have a unique absorptivity at a particular wavelength. Again, it has to do with the energy of each wavelength, and the allowable energy shifts within each molecule or atom. So we need a monochromator from last lecture, which is a unit used to allow to diffract light into multiple wavelengths and select light with a singular wavelength to get to your sample. So in this case, it is A and B, and then A and C, sorry. B is only correct for UV, not for fluorescence. For absorption, not for for absorption, not for fluorescence. UV is for both. UV vis is for both, but yeah, get it? We'll talk about why the transmitted beam is not the one measured for fluorescence later. Okay. So we either go with absorption or go with fluorescence when we are analyzing or using a method to either get qualitative data, which is just to check the presence of something or identify, or get structural elucidation. So you get qualitative data. A lot of the IR work is qualitative, for example. IR spectroscopy is qualitative. The identification of presence of caffeine in the lab was qualitative, but we did a step further and we did quantitative analysis. So to measure absorption or fluorescence, you need to have a compound that will actually be able to absorb light. It's kind of a necessity. It needs to absorb light. Glucose, does it absorb light? It doesn't. Whereas an isoflavone, does it absorb light? It does. So some molecules have the inherent signal, can absorb light. Other molecules do not. So, but those that do not, do we just leave it as is? No, we would make it happen. The way we make it happen is we induce it chemically. We take this glucose and force it to change into a compound that can absorb light by a series of chemical reactions involving enzymes as well. So we can use spectroscopy, UV-vis spectroscopy, to quantify macro components, large components. An example is the total carbohydrate by phenol sulfuric acid method that you're going to do in the lab in a couple of weeks. Quantification of microelements, there are a huge array of them. For example, the thiamine fluorometric method. You're not going to do this in the lab, but we're going to talk about it in the vitamins lecture. Enzyme-linked immunoassay, we'll have a lecture on that, but we're not going to do in lab. ELISA, but this is mostly to determine an array of compounds mostly used for allergens, but it can be used for mycotoxins, for example. It can be used for pesticides. It can be used for so many different applications. And it is based on having an absorption reading at the end where you have an enzyme, you add a substrate, gives you a product, and you measure absorption. Okay, so let's look at how absorption is measured and how it can be converted to concentration. So usually you have your solution. You will do that in the total carbohydrate assay. You will prepare your solution and you'll transfer it into a cuvette, and then you want to measure absorption at a particular wavelength. So you put the cuvette in the path of the light. So this P0 is the incident beam that's hitting the sample or the cuvette. And then this light that is leaving, we call it the transmitted light. Okay? So the amount of solution or the amount of analyte in your solution will affect the amount of light transmitted. And this light transmitted in absorption spectroscopy will be the light detected by the detector. So this is the light that is going to be measured, but there are going to be logarithmic equations, calculations to convert the transmitted light to an absorption. And that is not simply the difference between incident beam and transmitted beam. So here's the transmittance. The transmittance is basically the ratio of the transmitted beam over the incident beam. It's a ratio. And the percent you multiply by 100. This transmittance is not linear with concentration. Because it's not linear with concentration, we cannot use it for quantification. So we want to find another term or function that is linear with the concentration. And this is where it says the fraction of the incident beam that is not transmitted does not equal the solution absorption. Why is that? Can anybody guess why? Why it's not a simple subtraction? Light goes in, and then light goes out, and then other light is being absorbed. Sophia? Thank you. Did you read ahead? That's good. That's good. So yeah, some light will be scattered. Some light will be reflected back when it hits the surface here. So you might have reflected light. You might have diffracted light. The light can be scattered because the particulates in your sample will scatter light. The analytes might scatter light as well. Not just absorb it, scatter it, reflect it, diffract it.
Is that like when you do in micro where you measure turbidity?
Yeah.
It's like the little, like, I don't even know what it's called. Is it the same principle as that?
The turbidity has to do with scattering a lot of light. So when a solution is turbid, it will scatter a lot of light, and it will seem like there's a lot of absorption, but not really, because much less light is being transmitted. So oftentimes you have a centrifugation step that you would do before an analysis of anything. You want to make sure you have a clear solution to get exact absorption data. So turbidity, it has to do with scattering of light. Yep. Good. So because of that, it's not a simple subtraction, because the light can take multiple different, the matter interaction with light can result into many outcomes, not just absorption. Okay. So if we look at the absorption and relation of absorption to transmission, absorption is the log of the incident beam over the transmitted beam of light, which is really minus log t. So this is the opposite. So minus log t. Minus log t is linearly correlated with the concentration. And that's why Beer's law states that absorption equal A for absorptivity, B is for your distance or the path length, and then C for concentration. Sometimes when you don't have standards to do standard curves, but if you know the absorptivity of the molecule you're after or measuring, you can get the absorption, calculate concentration if the absorptivity is known. So you don't always need a calibration curve. So the concentration can be in any different unit. It can be molar, millimolar, milligram per ml, percentage, any unit. And the path has to be in centimeter. And the, A is absorptivity, which is per centimeter and concentration. And the absorptivity, when the concentration is in molarity, then it will be called molar absorptivity or molar extinction. Let's see here. Absorptivity is a proportionality constant. It's a constant for every molecule or atom, dependent on wild guess. Oh, that's a good wild guess. The molecular properties of the species, every molecule or every atom, if we want to talk about the atom species, will absorb differently based on its components, based on its allowable energy levels. So absorptivity will depend on this one. It will also depend on the wavelength. At every wavelength, you have different absorptivity based on the energy of that wavelength. C, chemical environment. So let's say you have a molecule that can dissociate, or you have a molecule that can get ionized. Ionized molecule will have different absorptivity than a non-ionized molecule. And the example for those of you that did the AA, we talked about the atom has to be measured in the atom form, not in the ionized form, because it will have different absorption. Okay, so it's all of the above. So oftentimes, you either have in a spectrophotometer, you either have a reference cell where you put a reference or a blank, we call it, and then you have another sample cell. Sometimes you don't have a reference cell and a sample cell. You'll just measure the blank and zero the instrument with the blank, and then measure your sample. And that's what you're going to do for that total carbohydrate lab. You will first start with the blank. The blank contains everything other than your sample. So the same reagents that went into the preparation of the sample will be present in the blank. So we need to use the blank to zero the unit, because the reagents might have an absorption. The reagents might scatter light. So you want to account for that. Then instead of using P0 as your incident beam, P becomes your incident beam. The P that is coming from the reference cell. So you'll have a reference cell, you will have the P, and that becomes the incident beam to your sample cell, because it corrects for anything that the reagents have that might diffract the light, reflect the light, scatter the light, etc., other than your sample. Here's the deviation. Oh, time's up. Emily was like, okay, done.